Okay, I think we'll start for today. So I would like to just confirm if I'm audible clearly to everyone. Hello. Can you please confirm if I'm audible so that we can proceed for today?
Yes,
Can you?
ma'am, you are audible.
Okay. Thank you. Thank you. Okay. So I'll introduce myself briefly. So this is Adyasha Sahoo from Electrical Engineering IIT Roorkee, where I'm working as a PhD scholar. So I am your NPTEL TA for the course Market Basics to Advanced Technology. So for this session, we'll be discussing about the week 3. First, we'll start with the overview of the course content for the week 3, followed by the Q&A session. And lastly, we'll see your doubts. Is the slide moving? I think it's not moving. Just a second. Okay. So these are the links for the course. You can mail me at the given ID if you have any queries. The so the slides are available in the Google Drive folder. You can find it after this session. The video will be also uploaded on YouTube, so you can see if you want. And lastly, I have the LinkedIn ID if anyone wants to connect. Okay, so this week we started with energy storage technologies. So we'll start with why do we need this energy storage systems in our grid? What is their role in our grid? You can answer based upon your understanding from the video recording, and then we'll discuss it in. Anyone? Some points are obviously on the screen. Okay, so I will go forward. So first one is grid stability and reliability. So as we know, the share of the renewable energy is increasing in our grid. So these resources, they are inherently intermittent in nature because they will be depending upon natural resources such as wind or sun, and they are not uh, what we can say constant in nature. So to handle their intermittencies, thus energy storage is a must. So this uh, grid stability and reliability, we can say that it can provide energy storage can help us to provide a stable capacity whenever it is required. Then also it will be helpful for peak load management. So as we know, these energy storage technologies, they can charge when there is abundant energy available and discharge in the time of high demand. So by that way, they can also help in peak load management. Moving on, they can also help for frequency and voltage support. So basically, whenever there is a power generation and demand mismatch, these storage technologies, they can charge or discharge accordingly to the need of the grid to make the frequency constant. Similarly, these renewable energies, they cannot provide, they don't have the capability to generate reactive power, but since they are always connected to the inverter based resources, so these inverter based resources, they can provide the needed reactive power for voltage support. Then moving on, we have grid resilience and black start. So obviously, since these storage technologies, they do not require a startup power as we require in case of thermal power plants. So they can also help in black start activities. Moving on, we have time shifting. So time shifting, we'll see it in the upcoming slides, but if anyone wants to share now, they can tell their views. So basically, time shifting and peak load management, they are kind of similar technologies, but we'll see in what way they differ in the upcoming slides.
Ma'am, time shifting means we will give rebate when the electricity demand is not there.
Hmm.
So people will use electricity at that time, and we will increase the tariff rate when the demand is more. So by this also we can manage the load.
Yeah, so that similar concept in case of storage, whenever it is of low demand or low prices, the storage can charge and discharge in the time of high prices to get benefits, I mean monetary financial benefits. Then moving to deferral of grid infrastructure. So, as we know, these penetration of renewables, what may happen in is during some slots there may be excess of renewables, excess of wind or excess of solar. So that may lead to excess of power injected to the grid, which will in turn lead to congestion of our lines. So to accommodate these renewables, we in turn what we have to do, we have to increase the capacity of our transmission system. We need extra lines. So if we have an energy storage in the in with a renewable, so when we have extra or excess renewables, this storage can charge, and this can in turn lead to deferral of grid infrastructure. And lastly, electrification of transport sector. So we know we are moving towards electric vehicles and hydrogen based vehicles. So for that, battery is the main for the electrification of the transportation sector. So we'll have a brief overview of the global scenario. Okay, so as we can see, the key regions where large-scale batteries have been actually deployed, and this data is based on 2017. There is Australia, there is China, Germany, Italy, Japan, and other countries. India is not advanced up to now compared to these countries, and the global installed capacity is around 10 gigawatt. Main services which these energy storage devices are providing, they are ancillary services for frequency regulation and voltage support. Then they are also providing capacity reserve. Then okay, capacity reserve, will anyone like to add what is capacity reserve? So basically what happens is, for managing our power system which is dynamic, always we need to have reserve with us, so that when we have need for power, these reserves can be activated. So the storage can act as a reserve, because we know due to the intermittent nature of the renewables. So this energy storage are must to provide adequate reserve, so that they can charge or discharge according to the need of the grid. So they will also provide firm capacity. So since these renewables, they cannot guarantee the power that there will be always some error based on their forecast. But what happened previously, they were thermal generators. So they provide fixed capacity or firm capacity, whatever. So whatever they had promised in the day ahead or through power purchase agreement, they will always provide that much amount of power. But in case of renewables, that may not be the case, because in real time, if there is low solar or low wind energy, they may not be able to produce that much amount of power. So in those cases, batteries storage will help to form the capacity in our grid. Similarly, they will also lead to curtailment reduction, because as we discussed, whenever there is excess renewable, we can store it. Then a reliable power to isolated grids. So if we are moving towards mini grids or microgrids, isolated microgrids, which are in far off or isolated places, so for those grids to have a regular amount of power at all times, storage will be a must in case of isolated grids. Then deferral of transmission and distribution of grids. So as we discussed, these storages, they will help in deferring the grid infrastructure investment in terms of let's say voltage control devices or transmission lines, substations. So the most established battery storage technologies in the present scenario is of lithium-ion batteries, and they are actually representing 90% of the total installed capacity. And it is because of the technology that is maturing and the reduction in its cost. So as we see, from 2010 to 2017, its cost has fell by 80%, which has led in turn to its increased addition in our grid. That the largest capacity project is in California, where we have a 300 megawatt battery and a 182 megawatt battery. So the examples of some leading battery manufacturers, they are GYD, Hitachi, and Samsung and Panasonic, as listed here.
Madam, what is the single battery specification?
Which battery, sir? Hello.
It must having certain batteries, na, ma'am, number of batteries. So
You are saying that capacity of each cell.
yes, no, cell is always two volt or 2.7 volt, but the one single battery. What is
Configuration wise of the largest capacity project you're asking, or what?
yes, like in our okay car, if you say there is 12 volt,
Okay.
35 ampere hour battery is a single battery. So similarly, here this this type of reserve capacity, what is the configuration of single battery?
So obviously that will depend upon, like, if we have battery banks, in what way they are being connected, their series and parallel connection. So that will in turn affect what is their current output and their voltage output. For that, we need to know the architecture or the arrangement, what is there in the battery bank. Okay. So moving on, I think. So, some more examples of large scale batteries in our grid. So we have a 100 megawatt battery by Tesla, a lithium-ion battery in South Australia, and its main service was frequency regulation and capacity firming. Similarly, we have a number of projects here. You can see in Germany for frequency regulation, in Italy for grid investment deferral and reduced RE curtailment. Similarly, in Japan and uh, Micronesia, we have these mini grids or isolated microgrids. So these batteries because what will happen in mini grids if there are no renewable to provide power to the consumers, we have to run degen generators. But if we have batteries, then we can charge the renewables in times when they are in excess, so that the dependency on the or the need of diesel generators is minimized. And basically, we'll try to see some numbers how these are transforming our power system. Basically, some studies have been conducted over the world to signify in like financially how much they are helping in cost savings. So for the Newark ISO, it has estimated that due to relief of transmission congestion, a 4 megawatt battery storage can help a reduction of $2.3 million of fuel cost they are able to save, and almost they are able to mitigate 400 hours of congestion in the grid. Similarly, in the New York, they are estimating $22 billion of savings in the bill if they are employing a 11,500 megawatt of energy storage. And these are proposed solutions or studies that they are doing before deploying the batteries. Similarly, we have for PJMs and other case studies. Then basically this is the duck curve, you must be aware. So can anyone explain me what is this duck curve, what it is trying to show you?
It is a real time load curve, ma'am.
Okay.
So in this, we have to see when the normal load is more, or where peak is more,
Hmm.
and where the demand is less. So where the demand is less, we have to store it, and where the demand is more, we have to feed it from the storage.
And similarly, also we have this ramp that is also crucial. So basically this duck curve, in the y-axis we have the load demand, and in the x-axis we have the time. Okay, so we can see that there is over the years how this duck curve is changing. So basically, previously we can see in the early years like 2012, 2013, this was what a nearly flat curve. But as the renewables have penetrated, we have got a huge ramp up requirement needed here and a ramp down requirement here, because during the power hours of solar, we can see there is huge reduction in the load demand because of the increasing penetration of solar PV. So this curve has come down. You can see the red line. It is for 2018, where the load has dropped up to less than 1.5 megawatt. And immediately when the solar hours are over, the demand is drastically increasing near about to 2.75 megawatts. So within this small period of time, we need to ramp up our resources. And this high ramping rate can be achieved by the storage because of their ability to inject power to the grid in a very short span of time. These high ramps can be effectively provided by the batteries. So you can see with the help of the storage, the blue line, we have achieved the blue line where when solar was abundantly available, the batteries were charged and discharged when solar was not there. This is a global plot for the share of various battery storage technologies. So we see earlier battery our lithium ion battery, it covered up to 40% of the global share, and lead acid batteries were also significant. But as the technology for lithium ion has matured over the years, there has been decrease in cost. As we were discussing, there was a decrease of about 80% of in their cost. Their share has increased rapidly, where mostly we have reached up to 90% of the total energy storage technologies. So leading we have lithium ion, some lead acid batteries, some sodium sulfur batteries, and rest 4 to 5%. There are other different types of energy storage. So this during your video lectures, I think you must have come across two terms, that is energy density and power density. So can anyone tell me what is the difference between these two characteristics for energy storage? Like we have some storage technologies which are of high energy type and some which are of high power type. So what does what do it basically means for a storage to be having high energy density? Okay, I think we'll see here. Okay, so energy density. So energy density is the amount of energy that can be stored per volume of the storage system. So basically, as it is written here, it refers to the amount of energy that can be stored per unit volume or mass in the storage system. So basically, its unit is watt hour per volume, that is meter cube, or mass, that is watt hour per kg. So if a system is having high energy density, we can say that it can store more amount of energy with a given volume or mass. So example of storage technologies with high energy density is our lithium ion batteries. So this makes them suitable because in a less space or less weight, these batteries can store more amount of energy. So these are important for applications of transportation, like for EVs, where you have to uh, install the battery inside the vehicles, so their weight will play a important role. Then moving on to power density. Excuse me. So if a storage technology is having to said to be having high power density, it means that it can charge or discharge very quickly. So basically it is the rate at which energy can be delivered from an energy storage system. So its unit is basically watt per meter cube or watt per kg, and high power density, it will imply that it can release the energy more rapidly. And the example of such technology is supercapacitor. So within seconds they can charge or discharge. So they are useful for the applications where we need high power delivery. So like this ramp up, if we need like high ramping rates in the grid, so these will be more useful.
Ma'am, any practical example of ramping? Because capacitor we discussed, it is not still what you say matured.
So yes, will come up. So what we need that sometimes some application, as we discussed for EV, we need high energy density, but supercapacitors they are having high power density. So as we see it here in the duck curve, maybe we need high ramping rates. So at that time we can use supercapacitor, but for that it need also to retain the amount of energy for this much period of time. So what is the solution for this is we will be moving towards hybrid energy storage. So what will happen in a hybrid energy storage is we'll be having we will combine two storage technologies, one with high energy, one with high power, so that as the application is required, we can use these bank or hybrid storage technologies. So we can have a lithium ion and a capacitor as a hybrid energy storage system, and according to the application, they can be used. So as we see here in the slide, there will be always a trade-off between energy and power density. So because of due to their inherent chemical or physical nature. So basically, you can see, for instance, lithium ion batteries, they are high energy density, but they have low power density because of their chemical reactions. Basically, when we say that it can ramp up very fast, it means obviously some chemical reaction has to be, there will be reversal or forward of that chemical reaction to charge or discharge a battery. So that chemical reaction in case of lithium ion will take large time. But supercapacitors, they are not electrochemical type of, uh, they are electrostatic devices. So as a result of which they can deliver the power rapidly. So obviously the choice of the energy storage will depend upon your application. And also we know hybrid energy storage devices where we use one high power and another high energy, and we combine them to get the best of both. So another key concept that you studied in this week was energy shifting versus peak shaving. So these two concepts, they are near about the same, but they differ over the objective, what they want to do. Although they are performing in a similar manner, but what they want to achieve or the aim of them is different. So, can anyone tell me what is the difference? Energy shifting and peak shaving. We discussed energy shifting here, no? So, what it will do, energy shifting, it will charge the batteries or store the energy when the prices of the energy are low, and it will discharge the batteries when the prices are high. So by that way it can earn the revenue. So this energy shifting, but what is happening that it will optimize the energy that has to be used over a time slot. So and peak shaving means during some particular amount of time where we have high load demand. At those times, we aim to discharge the battery to feed the loads, and we draw the power when there is low load. So here what we aim in peak shaving is to reduce the demand during a particular instant of time, but energy shifting is over a period of time. We want that energy to be consumed, but we optimize it in which slot we want to consume the energy. In some like low price slot, we try to store the energy, and high price slot we'd like to consume. So we are flexible, and over a period of time we are optimizing our decision. But in case of peak shaving, we know that during this time there is high load. So that particular time we have to discharge our battery, and during low load we have to charge our batteries. So we see energy shifting, they focus on optimizing the energy consumed over a period of time. So taking the advances of price fluctuations to earn more revenue. And peak shaving, it targets to reducing peak power during a particular time slot. So obviously coming here, the choice between these two strategies, it will depend upon what is our objective and what is our energy management strategy, what is your goal. Combining both this strategy will result in the most effective energy management process. So I think some optimization model was there in one of the weeks. So the equation that were used was energy equation for the battery. Then these were binary variables because we are trying to model the behavior of the battery. So in a particular instant, the battery may either charge or it may discharge. So these are both binary variables. So they can be 0 or 1. So by enforcing that it will be less than 1. So what all states can be possible here? If we're saying these are binary variables, what are the possible values for these? They both can be 0. In this case, this equation will be satisfied, or either of them can be 1. So either the battery can discharge, or it may charge, or it may not do both. It may stay idle, but it will not charge and discharge simultaneously. So to take care of that relation in real life, but the mathematics obviously doesn't understand it, we have to enforce it in the form of constraints. So this constraint will prevent the simultaneous charging discharging, because if both will be 1, it will be 2, and this equation will not be satisfied. Equation, not constraint, will not be satisfied. And obviously we want that at the end of the period, the SOC that is remaining in the battery should be certain percentage of the rated, maybe 50%, maybe 80%. So let's say you are optimizing over 24-hour interval. We are enforcing that at the end of 24 hours, this much amount of battery SOC should remain in my battery. So this constraint is used for that. And this is, I think, a relation for depth of discharge. It is not a part of modeling, optimization model. So also, I think the other key terms for battery life that we studied was calendar aging versus cyclic aging. Cycle aging. Anyone wants to say something about this? So, calendar aging, it is in long term. Also, it is known as time-based aging. So, it refers to the aging process even when the battery is not in use. Even if it is staying idle, some reduction in its life will take place. This is because of the chemical process that is occurring inside the battery even when we are not using it. So, that is calendar aging, and it will happen gradually over years. So the factors that are affecting the calendar aging, they are temperature. Obviously, if the battery temperatures are high, they may accelerate actually the chemical reaction, leading to faster degradation of the battery. Coming to SOC, so if you have very high amount SOC or very low extremes basically, then they can also contribute towards calendar aging of the battery in a long run. And chemical reactions. So as we discussed, even when the battery is idle, the chemical reaction within the battery electrodes and electrolyte, they will continue, leading to their gradual degradation. So this process is known as calendar aging. Whereas when we come to cycle aging, it is the aging due to the battery when it is in use, when it is running. It happens because of the repeated charging and discharging cycle. So each during each charging or discharging cycle, there will be a irreversible loss in the capacity, and over times, what will happen? This loss will added up, and they will lead to reduced overall capacity and performance. So the factors that will affect actively the cycle aging, they are depth of discharge. So deeper the discharge cycle or DOD, obviously that will lead to faster cycle aging. Also, charging rates, they will contribute to cycle aging. High charging rates will lead to higher stress and it may lead to faster aging. Similarly, each battery will have some protocols for charging and discharging, so they need to be followed. And if you are not following these rules, then one may accelerate the aging of their batteries. So both these calendar aging and cycle aging, calendar over a long period, and it will happen even if you use it or you don't use it. But cycle aging will depend upon how you're utilizing the battery. So if we compare them, to mitigate the calendar aging, we need to manage the temperature inside the battery, so moderate temperatures, and avoid extreme SOC levels during their storage. Similarly, to avoid cycle aging, we need to have lower discharge cycles and avoid the rapid charging and discharging that we are doing. And obviously, we need to follow the rules of the manufacturer. Then coming to calendar aging, so as we said, it regardless how you are using the battery. So even if you are not using it frequently, it will experience some loss in terms of its capacity due to the calendar aging. And cycle aging, so it is directly related to the number of charge and discharge cycles of the battery, like how you are using it. And frequent cycling will lead to gradual loss and reduced performance. So both these aging processes will contribute to the degradation of the battery performance, and we need effective battery management technology or management system to control their temperatures, to maintain their charging discharging strategies, and to extend their lifespan of the batteries. Then we saw the capability curve. So will anyone like to say something about the first type of capability curve here? So we have two, I think, trajectories that are being followed here. So what is basically a capability curve here? What we are representing?
It is active and reactive power.
Huh. So as we are seeing on the x-axis, we have P generated, and on y-axis we are having a Q generated. So by looking this capability curve, can we say that whether it is for a battery or it is for some other generating resources like your thermal generators? Can we say, can you infer from this capability curve that what is the resource we are talking about? Like this is the capability curve for which resource? A thermal generator or a battery? I think I may help you. Look at the x-axis. Here we are having P generated. So we are having some positive P generated, we are having some negative P generated. Negative P generated means it is P load. So with this feature, can we identify what it is?
And second one is battery. First one is thermal generator.
Which one? You say this one is a thermal generator?
Yes, ma'am. Yes.
So how can a thermal generator generate negative power?
We will not use that type of that part of the curve. We will use only positive one.
Yeah, so here we have the complete four quadrant operation. So this cannot be for a thermal generator. See, these two curves, they are different, but the operating line these two figures, capability curves, they are the same. The operating line or their operating region is different. See, both have four quadrant operation. So this type of operation can only be for batteries, because for synchronous generator we cannot have this part where there is negative P generated. But for batteries, as we discussed, they can charge or discharge. Basically, when they are charging, they are load, and when they are discharging, they are generators. Similarly, they can also similarly inject or consume the Q according to the requirement. So both this round capability curve we can see here, they are both for storage or batteries. So the maximum, or you can say the boundary, they are bounded by the maximum P generated, negative of maximum P generated. Similarly, maximum of Q generated and negative of Q generated, which gives us a circle. So here we are having a line. So this line is representing a constant power factor. Constant power factor means the ratio of P is to Q is same. You can see at each operating point, the ratio will be maintained same, so that the power factor at the point where it is connected is maintained. So this type of operation we see constant power factor operation. And here what we have, constant Q. We have fixed the Q to 4 and we are varying the P. So this is a constant Q or constant KVR operation. And mostly what we have is constant for constant active power or constant kilowatt. What will be the trajectory? Similarly, if say I fix the generation to zero point 0.6 per unit, then it will be a straight line parallel to the y-axis. So at each point, the P generated would be 0 0.6, but they will vary in the amount of Q. So this capability curve basically represents how much P and Q a battery can produce. So we
Ma'am,
cannot,
sorry to interrupt. Ma'am,
yes,
would you like to tell me that how battery can supply reactive power
yeah,
during the discharge?
I am not actually getting how it will provide in the sense.
Ma'am, how it provides reactive power during the discharge? Battery storage, ma'am.
So we'll be having inverters with this. So the inverter operation will give the reactive power, right? So how basically means, what do you mean? Actually, I'm not getting your question.
Ma'am, as battery is a resistive igniter, so that it will share the power of active. So how it can be
Is battery a purely resistive? If you have seen the equivalent circuit,
as well as I think capacitive as well.
okay, R and C component. So basically, these batteries you will be also having with them. They will store energy in the form of DC power or AC power.
Yes,
Hello.
ma'am.
The batteries, they are storing the energy in the form of DC power or AC power.
Ma'am, DC form.
So obviously, when you need to convert it into AC, you'll need a inverters there.
Invert. Yes, ma'am. Obviously.
So basically, that inverter capacity will decide how much Q you can provide. That will come from there.
Okay, ma'am. Okay, ma'am. Now I got it. Thank you.
Okay, thank you. So what I was saying that yes, depending on the operation, like if you are saying that in constant kVr mode you're operating, let's say at zero point 0.4 kVr, then the amount of P that can be generated is not perfectly 1 per unit. It is somewhat less. So this is the significance of capacity curve. So it will tell that how much P and Q both you can be providing at a time instant. Then next we had an important battery management. So can we can see some of the operation or the need for this BMS, but still if anyone wants to add to their thoughts, why it is a crucial. So we can see there are a number of operations here. Firstly, we have state monitoring and control. So what all features we need to monitor in a battery? Can anyone share me? What all parameters we need to monitor or what all states? So I'll say, SOC, SOH, then there is voltage, then there is current, then there is temperature, then there may be the over current or overcharging. So these all parameters we need to monitor in a battery for their optimal operation. And cell balancing. Can anyone tell me what is cell balancing? Why it is required? So I think we'll see it in detail in the next slide. But what was your understanding from the lecture? What is cell balancing? So, okay, we'll see it in the next slides. Then thermal and safety management. So it is very crucial because we know that nowadays when we are having these EVs, due to this thermal safety, sometimes we are getting the news that there has been incidences of fire. So we need to monitor the temperature inside the battery to avoid such situations or avoid the cases of overheating of the batteries. So to do that, we may have cooling systems inside our batteries. So basically, there will be sensors inside the battery who will sense the rise in temperature, and then they'll be having provision of, let's say, cooling facilities, such as they may have insulating materials so that they can dissipate their heat. There may be external fans and coolers which will try to maintain the temperature at the ambient one. Then coming to optimal performance. So what this battery management system will do, as we know inherently when we are having a combination of cells, some of the cell may have different voltage and different SOC levels. So the battery will ensure that they are same and they are charged and discharged at a same rate for their optimal performance. Then the next operation that is done is data logging and reporting. So why we need to log this data is to uh, perform some studies from this data, like for battery analysis, battery chemical process, or health analysis, or SOC estimations. We need data. This BMS, it can store this data and report it to us so that we can carry out the studies required. Then moving on, communication. Obviously, this batteries, they will sense the temperature, or let's say voltage, current, and they will communicate it to the master station, or as we say, so that, or the control centers, so that they can take the necessary action required. And obviously, when we are maintaining like the batteries at same SOC levels, and we are charging and discharging at the same same rates, and we are controlling the charging rates, we are controlling the temperature. So these all will lead to enhanced lifespan of the batteries. So due to this number of reasons, the BMS is crucial for the battery. Cell balancing, as we were discussing. So briefly, one two lines, anyone can say what is cell balancing, why it is required. My slides are moving, right? Okay. So what we have is, we have banks of interconnected cells inside a battery, and due to their manufacturing or inherent nature, they all may not be at same state. So we need cell balancing so that every cell is having equal SOCs. For that we need cell balancing. So the number of benefits that we get due to cell balancing, they are obviously maximizing the battery lifespan, because what will happen is, if they are at different SOC levels, and you are, let's say, giving, let's say one battery is at 10% level, one is at 60% level, and you are giving them the command to charge, then the 90% one may be harmed due to overcharging. So to avoid these circumstances, cell balancing is necessary. So, and it will in turn lead to maximizing the battery lifespan. Similarly, leading to energy efficiency. Okay, they will lead to enhanced efficiency, because as I said, we'll be having uh, the charge and discharge rate, when they'll be having same SOC levels, they'll be having efficient operations. Then enhanced safety. Obviously, if they are having different levels of SOC and you're charging one, it may again lead to stressing of the batteries with lower or extreme higher SOC levels. So this stress may lead to thermal runaway of the batteries, and hence we need to balance them for their enhanced safety. Then voltage stability, obviously. So by cell balancing, what will achieve is, we'll be avoiding the problem of over voltage, and they will have uniform charging and discharging process. So safety compliance, as I discussed here, safety, and overall we can say the system performance will be enhanced. So there are two types of balancing as you studied, passive and active. So we'll go through it one by one. So firstly we have passive cell balancing. We'll discuss about it. So in the passive cell balancing, it will try to redistribute the excess energy from the cells with higher SOC or higher voltage level to lower SOC or lower voltage. So in passive process, we are not actively transferring the energy in and out from the cells. Instead, we are dissipating this excess energy through the resistors or other passive elements. So the advantages of these are passive balancing. Obviously, these circuits are very simple and they are cost effective because we need only resistors to dissipate the excess energy. You don't have power complex electronic circuits like switches, and since there is no active transfer of energy, there is no additional energy consumption leading to their efficient energy. The disadvantages of such a passive cell balancing is that it will uh, be slower in bringing the cells. It is a slow process compared to the active methods because we are not transferring the energy but rather slowly dissipating the energy in form of heat here. So since obviously we are also wasting the energy in the form of heat, it will lead to lower efficiency. And with the passive cell balancing, it is effective when the voltage or SOC levels are not very large. The difference is not very large. So it has limited balancing range. So it is suitable for the application where the cell voltages they are not too large and a slower balancing rate is acceptable to them. Overall, this is a simple and more cost effective way. Moving on to active cell balancing. So in the active cell balancing, what we have is we are transferring the energy between the cells to make their SOC or voltage levels equal. And this we are achieving with the help of electronic switches, which will, or electronic circuits, which will control the flow of energy in and out of the cells. The advantages of this active cell balancing is it is a faster balancing process, so it can rapidly bring the cells to similar SOC or voltage levels and it will lead to improved performance. They are also having higher efficiency because the energy is not wasted here in the form of heat, and uh, we can we can make use of active cell balancing when the difference in the voltage or SOC is very large. So the balancing range is wide in the case of active balancing. The disadvantage is that these are complex electronic circuit and these are obviously costlier. Then some energy will always be consumed when we are transferring the energy between the cells. So it can lead to lower efficiency. So active cell balancing is preferred in the cases where we need rapid balancing of the cells. Like quickly we need to balance the cells and when the cells have higher differences between the voltage levels. So active balancing is more efficient and effective in these cases. So moving, I think we'll conclude that how we can add this utility scale devices in our grid. So we'll conclude the session here by looking into these. So firstly, we need some technical requirements. So, will anyone want to share their thoughts that how we can deploy these technologies, what all reforms we need to have, or what are their views on these energy storage technologies? Okay, so firstly, we need to have the technical requirements, that is, some hardware as well as some software reforms. So, we need to have the battery management system to protect the battery, and it will act as a controller to implement the charging and discharging algorithms. Then we need reforms in terms of policies because we need to have incentives to make these electricity storage projects. Also, we need to include them in long-term capacity expansion plans, in long-term planning problems, and we need also pilot or we know there are small these are small scale projects that are carried out and learn from them. Then also we need some regulatory requirements. Basically, we need these battery storage systems to participate in the ancillary service markets, and they can be generating revenue from this accordingly so that they can support in the system stability and control and protection. And they'll we also need to develop the billing and metering methods for these large scale utility connected batteries. Then we also need to incentivize their long term contracts. Then coming to the transmission and distribution systems, so these will reduce the overall investments and the generation they will defer the investment in generation capacity, in network reinforcement, and they'll also provide ancillary services to the transmission and distribution system, and they can generate revenue from them. Then also we need some stakeholders, some regulators who will take care of this battery store so that these battery storage projects are included in their long-term plans, and they need to provide the clear regulations for the ownership and how these storage systems are going to be operated. So these four reforms we need currently for the adoption or deployment of utility scale battery storage projects. So uh, I think we'll move to the question and answer session. So I'd like all of you to actively take part in this session. You can unmute and speak, or you may type in the chat box the answers. So the first question is, which of the following is not a type of mechanical energy storage system? So you have compressed air, you have gravity, pumped hydro, and latent. Hello, we are getting one latent. Anyone else? So, Mr. Rajneesh Tiwari sir, would you like to say why you think latent is not mechanical energy storage? like under which category it comes, if not mechanical? So we all know compressed air, where we store the when we have excess energy, we'll compress the air and store it in form of mechanical energy. So this is mechanical energy, compressed air. Then it is gravity, then pumped hydro. These are also types of mechanical energy source storage systems. Latent in other, what happens, the correct answer is obviously latent, as Mr. Rajnish had said. What happens in latent energy system is we have phase changing materials here. So what will happen, let's say for example, when there is high energy, the solid material may be changed to liquid state, and again when we have lower energy, this process may be reversed, liquid to solid. So basically there will be phase transformations in terms when we are using latent energy storage system from one state to other state while charging or discharging. So the correct answer is latent heat. Then the second question. So which of the following combination of energy storage technologies are not feasible for hybrid energy storage system? We have supercapacitor and battery, lithium ion and sodium sulfur battery, vanadium flow and lithium ion battery, or none of these. So we talked about hybrid energy storage system, right? These are combination of high power and high energy density types of storage system. So one high power and one high energy density technology, they are integrated to form a hybrid energy storage system. So accordingly, can you then identify which of these is not having such a combination of one high power and one high energy? Will anyone like to take a guess or answer if they know? You may type in the chat box, that will also do. So basically we know supercapacitor and battery we discussed. This is high power, this is high energy. Lithium ion is again high energy, sodium sulfur is high power. This is again high power, this is high energy. So basically all these are hybrid energy storage systems. So the correct answer is none of these. Then we have a matching type. So chemical, can we say which one of these stores the energy in form of chemical energy? So chemical is fuel cell. Then moving to mechanical. I think mechanical we all discussed. So it is flywheel. Electrochemical, you're having batteries with cathode and anode and electrolytes going chemical reactions. So battery is in form of electrochemical. And lastly we have electromagnetic, that is superconducting magnetic energy storage. So this is the answer. So A is with 3, B is with 1, C is with 2, and D is with 4. So can anyone tell something more about this fuel cells? Any kind of recent technology that you have heard? So are you aware of hydrogen, green hydrogen as a solution? Even our country has a green hydrogen mission plan. So basically, hydrogen and green hydrogen, they are different. So there are like gray hydrogen, blue hydrogen, green hydrogen, depending upon how we are producing this hydrogen. So gray hydrogen, basically it is a byproduct in steel industries or large scale industries. So when it is produced from as a byproduct in these industries, it is a gray hydrogen. But green hydrogen is the hydrogen that is produced by the electrolysis of water using green energy resources or renewable resources. So using this power from this green energy resources, when we do the electrolysis of water, we get the byproducts as hydrogen and oxygen. So basically this oxygen is, we all know it is not harmful, and hydrogen. So due to this process, it is being widely promoted. And what is that we can store this green hydrogen in ammonia tanks in the form of ammonia, and when we have excess generation we can store it in the form of ammonia, and when we need we can then have a reversible reaction to generate power. And this ammonia, it can be also transported in the form of trucks at the point where it is required. So due to these benefits, this hydro oxygen can also be again reused. And so due to this efficient process, we can say we are not getting any hazardous byproducts. So the nation is now moving towards, or it is incentivizing the green hydrogen projects. The next question is, which of the following storage type has high energy density? I think in the previous one we discussed here. Can anyone of you answer this? Which is a high energy density? We talked in detail for this. Supercapacitor is high power type. So because it is storing in the form of electrostatic, it can quickly re-inject or absorb. Flywheel also same, mechanical, so it is high power. Then lithium ion is high energy density, we discussed. So which has led to its lower weight. We can store more amount of energy in less weight, so that we are using it in EVs or other portable devices. Again, lead acid battery is not high energy density. Then a short actually numerical or problem. Yeah, I think Rajneesh has answered it. Lithium ion. I'm sorry I couldn't acknowledge you. You were right in the previous one. Lithium ion batteries of high energy density. Thank you, Rajni. Then the next question, a 12-volt battery with capacity of 500 ampere hours. It is at 80% SOC. So find the DOD. So this is the direct relation actually. SOC equals 1 minus depth of discharge, or the vice versa. So what will be the answer, everyone, please? So basically it will be, so basically it will be 20% if the SOC is 80%. Then next question we have, a 12-volt battery with a capacity of 500 ampere hour is again at 80% SOC. So calculate the energy that it's stored right now at 80% SOC. So what we are saying, 100% should be, 100% is 500 ampere hour. So what is 80% SOC? Can anyone calculate? This will be 400 ampere hour. Then coming up, which type of problem is a distribution network planning problem? Linear programming, mixed integer linear programming, mixed integer nonlinear programming, nonlinear programming. So these are types of classical mathematical optimization technique, right? So can anyone tell me basically what do you mean by this linear programming, MILP or MINLP? By the name, what we are trying to suggest? What type of problem? So basically, an optimization problem will have a objective function with which we are trying to optimizing, which is our objective is, let's say, minimize. It will be subject to, we are optimizing, let's say, with respect to the variable x here. So we'll be having some equality constraint. So those are a function of the variables. So these are f of x is a equality constraint, and we'll be having inequality constraint. So what this problem tells us is we are trying to minimize the subjective function j with respect to the variable x subject to the equality constraint f of x and subject to the inequality constraint g of x. So when we say linear programming, we say that all these expressions, they are linear functions of type. When we say linear means of a1 x1 plus a2 x2, where these are constant or parameters. So when we say linear programming, we mean this, that the variables, the function of variable, they are linearly related. So as we discussed in one of the slides, if you remember, this one, so we had a binary variable, means they can be either 1 or 0. So in case of mixed integer linear programming, we are telling that this is having binaries. The problem, we are having binary variables with us and they are linearly related. Mixed integer linear programming. In case of mixed integer non-linear programming, what we mean to see that we are obviously having binaries plus we are having non-linear equations. What do we mean by non-linear equations is we'll be having some terms like x1, x2, like multiplication of variables or division or power. So these are non-linear expressions and these are linear ones. So when we are telling MINLP, we are telling that these expressions, they are non-linear expressions and we are also having binary variables in that problem. Then non-linear programming. What we are saying here that we have non-linear expressions but we don't have our binaries. So in the slide we saw that to model the battery we need a binary, right? We need binary variables. So our problem will always be a mixed integer type. Am I correct? So could you understand up to this? Or if you have any doubt, you can please ask me. Anyone will please unmute and interact. I think I will be able to resolve it very better. So was it clear up to this that our planning problem, number one, it will have binaries. So this is not the option. This is not the option. So either it has to be MILP or MIMLP. So are you aware about power flow equations of the power system? Power flow equation. So to model our distribution network planning in this constraint, we need to have active and reactive power flows. So those are non-linear equations because we have multiplication of variables here. And also we have trigonometric terms here. So which makes them highly nonlinear. So we also have this is the for P active power. Similarly for reactive power, you will be having sign component here. And these power flow equations you need to have as constraints in the distribution network planning problem, right? And as I said, these are highly nonlinear due to the presence of multiplication between the variables plus due to the presence of these trigonometric terms. So our problem is also a nonlinear. So the right answer for this will be mixed integer due to the batteries, and it may also be due to other considerations. So binary and this power flow equations they lead to nonlinear type problem. So our problem is a mixed integer nonlinear type problems. So moving to the next question. So select the advantage of mathematical programming approach, that is classical optimization, low computation, global optimal solution, short convergence time, or simple formulation. Which is the advantage of classical mathematical optimization? So computational burden and convergence time, they are not even same. But what they have is accurate solution. That is, we can achieve global optimal solution. So do you mean by this global optimal and local optimal? So basically, if we have a function which is highly nonlinear as our power flow, so this may be our trajectory. So what will happen is if you find the minimum of this function, then it will be at this point, which is your global minima point, right? But due to this non-linear type of problem, sometimes it may so happen that your solution is trapped in the local minimum, like here. So the classical optimization technique, they can identify the global point, but other heuristic methods, they may trap in the local optimal point. So as we discussed, this non-linear programming which we discussed in my NLP, for this the solution may trap in the local minima type. And finding its global minima, it will be uh, uh, we need high computational burden, and it will take more time to find the solution. So for the power system applications where we need faster decisions to make, we what we do is we simplify our problem. So how we simplify this nonlinear terms, we linear make them linear. So we linearize the problem so that we get MILP, and this MILP, they can be solved by the commercially available servers. And what will happen in linear type problem, you'll the what you'll be having is like this. So you'll get the solution faster. So MILP, it is non-linear, it is non-convex. So when we need faster solution, we may linearize this MILP to get the global optimal solution. Then the last question for today. The indication of state of charge of a battery is best given by specific gravity, temperature, color, or level of electrolyte. So we know in a battery we have a electrolyte, we have anode, we have cathode, where some electrolysis process is taking place. So using which one of the property of the electrolytes can we estimate the state of charge? Will anyone like to take a guess? Obviously, it won't be color. By the color, you can't say anything. The level of electrolyte will also not tell you. The temperature of the electrolyte may be due to various other reasons. So it will be due to the specific gravity. So what do you mean by specific gravity? So basically, it will tell the concentration of the chemicals inside the electrolyte. So by knowing the concentration, if high concentration, it may imply from that the level of SOC is high or low. So the concentration of the chemical present can indicate the level of SOC in a battery. Then any doubts from the session? So in one of the week's lecture, there will be a case study for optimal battery placement. So can anyone tell me why we need this kind of study? Why do we need a optimal battery placement problem? So basically, what happens is for a given system, let's say for an endless system, let's say we have a radial network here with some buses. So maybe, so why we need this optimal battery placement is, let's say we have such a system here, and these batteries, they are costly to deploy, they are not easy to install, right? Or like the financial that is associated with it. Let's say for this one system, we have a financial incentive, or the money that we have is to install, let's say, two batteries or two energy storage systems. So how to decide at which bus we need to deploy this battery for the optimal operation of this whole system? So for those kind of studies, we need to have the battery placement problem, where first we'll carry the online studies. So this battery placement problem, it will be modeled in the form of binaries, similar to optimal PME placement if you have heard. So we'll be having binaries, and our objective may be cost minimization. So we'll be having some excite and CI, and subject to, there will be power flow equations, then there will be power balance equations, then there will be capacity. Let's say we got funding for 5 megawatt hour, so there will be limit on this capacity, and we will take the input as the forecast for generation and load, and we may perform a yearly study to identify which is the optimal position, or which bus is the optimal position for this energy storage device to be deployed. So for that, these yearly study will give the placement location. So maybe this optimization model may say one here and let's say second one here. By deploying this, we'll get the optimal operation of this system. So for this, it is necessary to carry out the optimal battery placement problem. So I hope it is clear to everyone. So any feedback if you want, any doubt regarding your previous assignment or for this course. So I think then if no more queries are there, okay, then we will close the session for today. So thank you everyone for your time and joining. So we'll meet in the next week.